type X, but in this case, you need to apply the perpendicular field to induce the switching. But for the type Y, you do not have to apply the field, and so you can solely induce the switching by the applying current. But in terms of the switching speed, because the precessional motion is required before the switching, so the type Y requires time to switch. Whereas for the type Z and type X, the switching takes place immediately after turning on the spin orbit torque. So in principle, a higher speed switching is expected for the type Z and type X. Okay. I think so. Yes, I noticed. So, sorry. So these two are opposite. Sorry. Thanks. So this should be here and this should be here. Okay. So I will correct this for the files in the Google Drive. Okay. And okay. So the spin orbital can also induce the magnetic domain wall motion, and this is the Satoru's work, so Professor Satoru Emori's work in 2013. But before their work, so this is the work by Professor Beach's team and Professor Parkin's team. But before that, this should be the first observation of the spin orbital-induced domain wall motion, although in this paper, there's no description about the effect of the spin orbit torque. So this guy attributed the motion of the domain wall to another mechanism. But I think that this is also induced by the spin orbit torque. Okay, and regarding the magnitude of the spin Hall angle, so this is the review paper. So what I'd like to say is that the heavy metal is better to obtain the larger spin orbit torque, and so far the tungsten is known to be a very good material to induce the magnetization to obtain the larger spin Hall angle. And this is also a famous paper by Chi-Feng. So they found that the beta structured tungsten can generate a very large spin Hall effect, whose magnitude is, the spin Hall angle is 0.33. So the larger spin Hall effect is observed in tungsten, having the beta structures. Okay, so let me quickly discuss what is the electric field-induced switching. So as I mentioned at the beginning, so this is also a famous paper by Hideo Ono's team in 2000. So because the magnetic properties is determined by the state of the Fermi level. So by accumulating or decreasing the charge in these capacitance structures, then they can turn on the magnetism and turn off the magnetism by changing the population of the electric charge. And indeed, they could observe the ferromagnetic properties and the paramagnetic properties at a constant temperature just by tuning, just by changing the electric voltage. So, and this was done at low temperature, 22 Kelvin, but the same phenomena was observed at room temperature in the metallic systems by French group. And in this paper, the magnetic phase transition was achieved by the electric field effect. And in this paper, a nice change in the magnetic anisotropy was induced by giving the electric voltage. And by using the voltage-induced voltage-controlled magnetic anisotropies, the magnetization switching can be achieved. And this is the paper by the team of the Osaka University. So they showed the magnetization switching in the in-plane systems, and the perpendicular magnetization can be also switched by giving the electric voltage. So this is this is all for the electric field effect for the to induce the magnetization switching. So the short summary, so the spin transfer torque, spin orbit torque, and electric field effect over BCDMA allows to manipulate the magnetization. The spin transfer torque can be understood by considering the transfer of angular momentum between the conduction electrons and local magnetization through the SD exchange coupling. And spin orbit torque is a spin transfer torque induced by non-equilibrium spin accumulation owing to the spin orbit interactions such as the spin Hall effect and Rashba-Edelstein effect. And the electric field effect changes the magnetic properties by modulation of the Fermi level by changing the population of the electrons or the electric charge. And not only switching but also oscillation, resonance, and manual motion, etc. are driven by spin transfer torque, spin orbit torque, and the electric field effect. Okay, so I only have 10 minutes, but do you have any questions? Actually, okay.
Thank you very much for your talk. I have a question about the SDT LG equation.
Mm-hmm.
I want to ask you, can you explain about the speed of SDT switching? I remember you showed delta M over delta T equation.
I see. Okay, so wait for a moment.
Yes,
this one?
this one. Yes. Yeah, I want to ask about how fast do you expect from this SDT switching?
Okay, so in the very naive picture, you can induce the faster switching by increasing the current. So the speed of the switching is proportional to the injecting current. So but in reality, the larger current should break your device, so there is some upper limit due to the technical reason. But the increasing the injecting current results in the shorter time for the switching.
Yes. So in this case, for example, if we want to use like low power and to protect our device and also save the energy, how is the level of the pulse you can use to switch the magnetization? Like it can be sub-nanosecond or even few picosecond?
As far as I know, the sub-nanosecond switching is achieved in probably the first one is by IBM time. So they showed the sub-nanosecond switching by the MTJ. But the stack structure is special. So if I remember correctly, they showed two layers sandwiching the free layer to double the in which the double spin transfer torque is expected. Okay.
Okay. Okay. Thank you.
And question.
Professor, so I have two short questions. The first is, in some of the paper of topological insulators, I have seen that they have mentioned the spin Hall angles, reported the spin Hall angles as greater than 1.
Yes.
So what does this signifies? Because spin Hall, this spin current cannot be, I think, greater than the input current, that the conventional current.
Yes. So the topological insulator is a very special case. So it's difficult to define the current because it comes from another mechanism. So the larger spin Hall angle beyond 1 is expected. But that cannot be explained by the current scenario.
That current formula, that JS by JC, it cannot
so,
be explained from that.
It's difficult to define JC. That's why the larger TM, larger spin Hall angle is expected.
And Professor, my second question is that the magnitude of the REE effect at the changed interfaces. So that interface, if the interface is of metal, and another interface is of metal insulator, so how the magnitude of the REE will be different in these two interfaces?
I see. Actually, I am not familiar with the theory of the Rashba-Edelstein effect, but so yes, so we have two interfaces. One is the interface with the oxide, and the other is the interface between the metals. And so, yeah, that's a controversial issue as far as I understand. So I think that the Rashba effect should be observed, should be there, both in the interface. So and the Rashba effect should be, Rashba-Edelstein effect magnitude is determined by the work function difference and the spin-orbit interaction. So it depends on the material system you use. That's my understanding.
So in which system it will be more, like metal insulator or metal-metal interface?
I don't know. So it depends on the specific material system. So it differs from the material to material.
Thank you.
Okay, so let me quickly go to the remaining part in the next 10 minutes. So, okay, so let me quickly explain why the Spintronics is promising in integrated circuit. So this is the famous Muir's law. So but now the end of the Muir's law is approaching, mainly due to these three reasons. One is physical scaling limit, and the other is standby power consumption. Now, even though the integrated circuit is not working, huge power is consumed in the standby mode. And another one is data transfer bottleneck. So because the logic and the memory needs to exchange the information frequently, so even though the logic and the memory becomes fast, the data transfer requires some time and also requires some power, and that limits the evolution of the integrated circuit. So these are the three serious issues. So let me jump to why the Spintronics is necessary. So if you have any questions for these slides I am skipping, please contact me. So I will be here until tomorrow noon. Okay, so to solve the issue of the integrated circuits, we need a non-volatile memory. But any non-volatile memory is not good. So the non-volatile memory must satisfy these conditions. One is that it is scalable, and it is fast, and it has infinite endurance to replace the existing semiconductor memories, and ideally has to have the back-end of line compatibilities, and can be driven by low voltage. And comparing the emerging memories, such as the phase change memory and resistive random access memory and magnet resistive random access memories, the MRAM is very promising in a sense that it can be operated with a reasonably small voltage, and it can be operated with a reasonably small time scale, and also its endurance is very excellent compared with these two rivals. So it is very promising to replace these volatile SRAM and DRAM. So this is why the Spintronics is expected to be a very promising candidate to make the integrated circuits low power. Okay, and so let me quickly discuss the history of the MRAM. So first product of the MRAM uses the Ampere's law. So by injecting the current, you can switch your magnetization by the magnetic field. And this type of the MRAM has been commercialized since 2006, but its application area is not so large. So it is limited in, for example, space or the airplane. The reason is that it requires a large current to switch the magnetization. So it only gets a very limited market. So people switch to the spin transfer torque type magneto-resistive memories. And okay, so let me skip. In 2012, the Everspin commercialized the spin transfer torque type magneto-resistive RAM, MRAM, using the in-plane material systems. But this also cannot get the huge market, mainly due to the less volume and less efficiency. So people think about to make it more efficient. And then we need to switch to the perpendicular system, because the in-plane system requires additional current to induce the magnetization switching for this is actually a very important slide. So for the in-plane magnet, to induce the magnetization switching using the spin transfer torque, this is the energy to save your information. So this is determined by the applications. And to induce the switching, the additional term is added. So you need the cost to induce the magnetization switching by current. But for the case of the perpendicular systems, this additional cost is not required. And that's why the perpendicular system is considered to be efficient to induce the magnetization switching. And this is a very famous discovery of the perpendicular magnetization at the interface between cold iron boron and NGO. And with this finding, the third generation of the MRAM has been commercialized since 2018. And so now you can buy the product of the STT-MRAM, for example, in the smartwatch. And now people are looking for the expansion of the MRAM market by using the 3-terminal version. And the reason why the 3-terminal is promising is that it can have the larger operation margin than the 2-terminal version. For the 2-terminal version, the read and write current paths are the same. So the operation margin for read operation and write operations is limited in this window. This is the case for the time-dependent dielectric breakdown. So if you apply the large voltage, then your tunneling barrier is broken. So the operation margin is limited in this window, but it is not the case for the 3-terminal structures, and you can obtain a larger operation margin. And this is indeed favorable for higher speed operations. And the 3-terminal MRAM has been demonstrated by several, since the first demonstration was done in 2006, and then, and these three utilizes the field-driven types, and these three utilizes the magnetic domain wall motion, and the lower three are the case to use the spin of torque to induce the magnetization switching. And from 11, the TSMC researchers will tell us the status of the SOT MRAM for AI applications. Okay, and okay, so I think I have. Okay, so please give me 5 more minutes to quickly discuss the future of the potential of the Spintronics embedded integrated circuits. So now, this is the cartoon for the current VLSI, in which the logic or core and memory are separated, and they are connected by the global wiring. But by replacing the volatile working memories by the non-volatile Spintronics memories, we can make it low power, so energy efficient. And also, because the Spintronic devices can be integrated on the logic circuits, so in principle, this von Neumann so we can switch the von Neumann architecture to the non-von Neumann architecture. And this is much more energy efficient in a sense that it can be free from the data transfer bottleneck. So we can realize a much energy efficient integrated circuits. And indeed, the Tohoku University team demonstrated several kinds of the integrated circuits in which the Spintronics devices are embedded on top of the integrated, the CMOS circuits. And we showed about 2 orders of magnitude smaller power consumption compared with the CMOS counterparts. And then, if we can have a more energy efficient integrated circuits, we can change the IoT societies. So now the IoT societies, IoT technologies, this is the cartoon for the current IoT societies. So many sensors are distributed around us, and the sensors collect the information and send the information to the cloud. But if we can use the Spintronics integrated circuits, then because the Spintronics systems can treat the information and communicate with each other because it's a higher performance. So we can reduce the information we need to transfer to the cloud. So we can reduce the information we need to communicate between the physical system, physical world, and the cyber world. So it is so that we can reduce the energy consumption for the communications. And also, because the Spintronics integrated circuit consumes much less power than the system without Spintronics, so it can be operated by energy harvesting, like energy harvesting. So we do not have to care about the exchange of the battery. So the maintenance-free IoT devices can be constructed by using the Spintronics integrated circuits. So this is also promising to expand the possibility of the IoT societies. So this is a very promising future opened by the Spintronics. Okay, and also the Spintronics systems, so in MRAM, the non-volatile nature, high-speed, high-endurance, scalable, and low-voltage and back-end of line process compatibility are used in the MRAM. But the Spintronics has many other unexplored functionalities like analog or analog-digital tunability and short-term memory functionality, non-linearity, stochasticity, and superposition and entanglement, so quantum nature. So by using these two unexplored functionalities, we have a chance to do unconventional computing. And so yesterday we learned that the analog feature can be useful for the artificial neural network. So we learned from Prem. And tomorrow we learned from Keren that the stochastic nature of the Spintronics system is useful for unconventional computers. Okay, so so these are the demonstrated neuromorphic computing with Spintronics, but I need to skip this. And so this is a short summary of the fourth part. So the VLSI faces several serious challenges, such as the physical scaling limit, increasing standby power, and data transfer bottleneck. And the non-volatile Spintronic devices is expected to be a promising candidate to address these issues due to the non-volatility and many other promising properties. And especially it is promising for the standby power critical applications for IoT. And MRAM, the market of the ST-MRAM is expanding with the cobalt ion volume geo-based perpendicular MTGs. The third generation STT-MRAM is very promising to get a larger market than the first and second generations. And now the SOT-MRAM is expected to apply for a higher level, higher speed cache memories. And also conventional computing is a very promising way that the Spintronics community to go. Okay, okay. So I'm sorry, time doesn't allow for the fifth section, but so I prepared the antiferromagnetic Spintronics. So electrical control of the antiferromagnet, electrical readout and control of the antiferromagnet, and non-collinear antiferromagnet. And so this is also the work for non-collinear antiferromagnet and the alpha magnet. And so this is my work. So the combination of the spin Hall effect and exchange bias should be give us interesting properties. So this is my personal view for the advantage of the potential advantage of the antiferromagnetic Spintronics, but time doesn't allow. So let me now finish, and I'm happy to answer the questions. Okay, thank you. Okay, so if you have a quick question, ask me. And if you don't have, so if you like to ask the questions, I'm here during the break, so come here. So now, do you have any questions? Okay.
Really quickly, what do you mean by back end of the line compatible?
I see. So, okay, I didn't tell you. I do not have the time. So, but back end of line process means that. Okay, so let me quickly discuss. So in the integrated circuits production process, there is front end of line and back end of line. Okay, so this is a good picture. So this is the cross-sectional view of the integrated circuit. So here we have the transistor. And this, the process to fabricate transistor is called the front end of line. And the process to fabricate the interconnect is called back end of line, or BOL. Fiol and BOL. And the MRAM and the MTJ can be formed in between the interconnects. So you can put the device on top of the CMOS circuit. So this is the BOL compatibility, back end of line compatibility. And this is not possible for SRAM or DRAM because the SRAM and DRAM should be fabricated on the same floor. Okay? So we need to adapt so that if you use the SRAM or DRAM, this von Neumann architecture, you need to use this von Neumann architecture. But if you use the MTJ, you can put your memory block on the logic. So you can drastically reduce the distance between the logic and memory. That's a BOL compatibility. Thanks for the question. Any other question? Okay, so we have 20 minutes break, so come here if you have any questions.